All right, next on our list is comets. Comets have been around for as long as we've been measuring such things as astronomical features. They sometimes get confused with falling stars. Falling stars when a rock falls through the upper atmosphere and burns up. These are not that. They appear in the night sky and they appear for months, oftentimes, as little burning flame sort of things in the sky. It's not all what they are, but that's what they do. Now we know, because we don't see them most of the time, that they must have orbits that do not look like normal orbits, and so that's what this first diagram is about. The orbits are elliptical, highly elliptical. They're hugely elliptical. They go out deep in space, then they come all the way back in. They go close to the sun, where they're speeding up, and then they go zipping back all the way out. All right? And again, some things they look like. So here's a close-up. Actually, let's just show what they look like in the sky. This is Hale-Bopp. Hale-Bopp. Notice it's got two tails. We'll talk about that in just a second. And then this is Lulin. This is my favorite comet because Lulin is completely confused. But whatever. Let's talk about what they look like up close. This is what they look like up close. Fortunately, the European Union decided to get off its rear end and actually approach a comet. So this is the Rosetta Comet. And as they approach it, this is what they look like. Chunky balls or whatever. They went even so far as to say that they landed on it and took some pictures from the surface. Now, it's not shocking. We knew what comets were made of. Comets are made out of ice, including water ice, largely. And then they're also got dirt, dust. Okay? Some sort of things that are in asteroids, some metallic dust, and also some carbonaceous dusts. And so, as we looked at these pretty pictures, as we see comets, what are they? How do they operate? Well, it is interesting because what happens is these comets come in from outer space, from very far out. Oops, this is not us at all. New. Want to do some chemistry? No? Let's not do some chemistry then. All right. So what happens is this. These things are out in space. Here's the sun. They come in an orbit that looks like this, which means they are very slow during this stretch. Right? The farther they're out, the slower they're traveling. As they come screaming closer, closer, so they go faster, 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 whip around, and then slower and slower, slower, slower. So Earth has orbits that look something like this, to give you perspective. And so why do we see these things at all? Well, first of all, how big are they? Maybe they're huge, right? We figure the average comet is about 6 miles in radius, which is not enough to see with the naked eyeball unless you are extraordinarily close to it. So therefore, this is not something that you can see because of that. What happens is these things come in, they get to about Jupiter, and they start to put off a tail. Now, I want you to see something. Let's say as I get past Mars, here's where my comet is. Now you're thinking, I know how a tail would work. A tail should be going this way. Turns out that's not the direction of the tail. The tail is actually this way. Why is the tail that way? That makes no sense at all. Why would the tail go off in that direction? As it gets to here, the tail would be this way. As it gets to here, the tail would be this way. And these things get blasted several Earth radiuses behind them. So what the heck? And even as it's heading back away, the tail's actually sort of in front of it. Whoops, it should be this way. The tail's sort of in front of it. And so what's happening here is the sun is microwaving the ice. And as it microwaves the ice, you know, because there's no atmosphere on a comet, because a comet's just a little tiny rock, essentially a ball of ice and snow, basically a dirty snowball, that that ice, the moment it starts to melt, actually has to turn into a gas, so it sublimates into gas, and that gas goes streaming off into space because there's no pressure. The gas stays very, very thinly spread out, and light on that gas is visible from very far away because these things end up being bigger than planets, these tails. And so after blowing off that much ice, there's clearly going to be less ice, and so then the comet goes off in the distance and you might think would die. Here's the thing, though. Halley's Comets come back every 76 years since at least the 1500s. In fact, we now have some people, Chinese historians, that say you can actually trace it back a lot earlier than that. If you do a reasonable amount of math every 76 years, go backwards in times, it was probably the comet that was over England, which caused the French to attack England on a very propitious moment and decide to take over England because they saw the sword of God in the sky. But again, 1,000 years before that, the Chinese were noting this thing that was going, this little sword in the sky sort of thing. So these have been going on for a long time. So how the heck is Halley's coming back? If it's only, Halley's a little big, I think it's about 10 miles across, so 10 miles in radius. So how does this thing keep regenerating? Like, it's blowing off planets worth of gas. It can't keep going around in circles. What turns out, what's interesting is when it gets out here, remember, it's going to spend very little time here. It's whipping around, and then slow. It's been a lot of time out in this range. Well, here's about where our friend Neptune is. So these things are going out past Neptune into the dim and distant distance. They must be getting a reload. Well, how does a comet get a reload? It must be collecting bits of ice and dust out here. How does it collect that? Well, because there must be ice and dust on a grand scale. The first slide I showed you had not just the orbital feature. Uh-oh, I'm not getting my little arrow so I can go backwards. Come on, really? So annoying. Come on. Oh yeah, it's going to draw. No, I don't want to draw anymore. I want to go left, right. Thank you. See this little glowy thing? This represents something called the Kuiper Belt. Scientist named Kuiper said, actually, if they're reloading, there must be ice out there. And there must be lots of ice because there's lots of comets. And there must be cajillions of pieces of ice out there, all in roughly the ecliptic with our orbits. And hence, when you look with a telescope designed specifically to pick up large amounts of little bitty bits of ice out in space, you find, in fact, there's something called the Kuiper Belt. And so things that are in that thing, most of them orbit in a nice pretty circle, going the same direction as the planets, drifting along, minding their own business. Ones that collide will get in a weird orbit that sometimes allows them to look like comets, and they pretty up our sky for us, which is awful nice of them. Now, that would be a complete story, but let's talk about some deviations of the mean. By the way, which way is the sun? This one's interesting. The sun is blasting the stuff off the surface, but you can see the stuff going off this way. Up close, more of the blast is on the front end. It's kind of funky, but whatever. Discussion for another day. Here, we've got the blast, so we know where is the sun? The sun's over here somewhere. It's blasting this off. What is this thin layer? Something called a solar wind. The sun whips around it some charged particles. Those charged particles don't come directly off the sun. They come at an angle from the sun. And so that's what this is another layer of heat blasting stuff off the surface. And it leads to a thin tail. Sometimes you see this double tail. What about my favorite? This is Lulin here. Lulin. Lulin is a really neat comet. Why? Because Lulin is prettier than the other comets. Look how pretty this is. And second of all, it's backwards. What? If all of the planets go in an orbit like this, Lulin's going this way. They're going the opposite ways, or darn close to it. Lulin is out of sync. Not only that, but Lulin has one other very nice feature. It takes about 45,000 years for it to do one orbit. Hear that? 45,000 years means you ain't going to see it again. It happened in 2006. If you missed it the first time, you're not seeing Lulin ever again. Lulin is a group of other comets. We have these pretty comets there that are sitting in this nice pretty line that do this sort of thing. But we also have comets in what is called the Oort Cloud. And the Oort Cloud sounds alien enough. It's actually just another physicist name. The Oort Cloud is way the heck out in deep space, and it forms a complete sphere around our sun. A complete sphere in every direction. So comets coming from the Oort Cloud sometimes go, like normal, but they also can come backwards. They can come from the North Pole of the sun and loop around this way instead, and go back out in deep space. What's true, though, is the Oort Cloud is so far out there, it's so far gone, that you're basically looking at comets that take at least 200 years, and actually that's an underestimation. Most of these are in the land of 10,000, 20,000, 30,000. Some comets that come from the Oort Cloud look like their orbits are so deranged that they may never actually, they're not actually in an ellipse, they're in a hyperbola, which means they're not coming back ever. Some suspicion is that whether or not that can happen, but there is some belief to that. So that's the Oort Cloud. Now, what do you need to know about comets? What you need to know about comets is comets have elliptical orbits. They are usually quite long. The ice and snow blasting off the surface, they're very small, but the ice and snow blasting off the surface makes a big enough tail for you to see it. For the most part, these are basically just dirty snowballs that recollect in something called the Kuiper Belt, which is where things like Pluto and Buffy and those sorts of things hang out. The dwarf planets hang out inside of that area of little chunks of ice floating out in space. And then farther out, there's something called an Oort Cloud. The Oort Cloud actually is so far out. Some people are saying that the end of the Oort Cloud is halfway between us and the next star over. That would be an immense distance. We're talking about distance that it would take our fastest probe 5,000 years to cover, to get to. So these are very far away. Very, very far away. All right, that's enough for comets.